basically based on the grade of the zener, the R sub Z, you can find zeners that will improve even above this 3.4%. The load regulation is asking, when the load goes from 15 milliamp to 0, how will the zener react to that? So the load regulation is minus RZ in parallel with R, so that's minus 9.7 millivolts per milliamperes. So to get an idea if this is a acceptable number, of course your next step is just to get your calculator and make a simple calculation. So here's our line regulation, minus 9.7 millivolts per milliamp. And if the load I sub L jumps from 0 to 15 milliamps, so it jumps full scale, the zener voltage, delta VZ, will change minus 9.7 times 15, minus 9.7 millivolts times 15 milliamp, minus 0.15 volts, and the zener voltage is 7.5, so we calculate a difference of minus 0.15 compared to 7.5, that's approximately minus 2% of the zener voltage. Now the note is, if the source jumps full scale at the same time the load jumps full scale down, then the error jumps up to 5.4%. So there's a worst case when the source, when the peak of the ripple is at the peak, and then the load acts for zero current, the error is going to go up to 4.5%. So this would probably be a circuit you could test in simulation, that you probably build it and use an oscilloscope and material to actually get a better number. But minus 2% to 5.4% might be acceptable if the load changes from 50 milliamps to 0 milliamperes. So designing a power supply, if we go back to the our starting diagram here, we covered the diode rectifier, the filter, the voltage regulator, zener diode, and we'll assume an arbitrary load. This schematic shows just a resistor. What type of rectifier is shown here? And we covered rectifiers on our last session. What's the name of this rectifier? There's four silicon diodes. It has a single capacitor. Here's our zener, and here's our zener resistor, and then there's a load resistor connected to it. Now this circuit uses a transformer. This is the line voltage input.
Is this a square?
Do you have a name for it?
Is it a square?
What is it?
A square?
A square. Its shape does have a square shape. It's called a bridge rectifier with four diodes. What's unusual about this circuit is that it has a differential input on it. Now, if you're taking lab 1, when we get to diodes, you'll actually be building a version of this circuit. And in order to build this circuit, we have to use an isolation transformer, which is a transformer that isolates from the 120 volt AC input. So if we're kind of paying attention now, and later when we cover this circuit in line 1, we'll recall that this circuit uses floating inputs, which means you can't measure these voltages across these two terminals here. with a multimeter because it's a differential input, so they're not referenced to ground. So just keep that in mind later on. So a circuit like this then, if we, let's say we need an 8-volt Zener voltage, so we search and we find 8-volt Zener diodes. We'll use a regular transformer. This transformer turns ratio is the number of turns between the primary and the secondary. So this is saying this transformer has a 1 to 10. So this is 120 volt AC. What's the voltage on the secondary? It's a 1 to 10. Inversely. Divided by 10.
800 millivolts?
So it will divide it when, it's not actually dividing. When you get into transformers, you get into electromagnetic theory of how these work. They'll actually poles of wire. So it will divide the 120 down to about 12 volts. Now, what is the peak amplitude of a 120 volt AC?
120 volts? That's good.
But what's the peak amplitude?
Peak to peak, or just?
The peak. And what is this? We're in the presence of these outlets everywhere. They carry 120 volts. What does that actually mean, though? It means don't tamper with it, of course. But what does it mean? And why is it so dangerous?
Oh, there's a lot of amplitude?
In the early days of the inventing alternating current, lots of individuals were electrocuted by it. And it's because AC looks for a path to ground. And it took a while for many to understand that if we touch AC, it's going to try to find a path to ground, basically. And today we understand basically that, so we stay away from the AC ports. However, at the bottom here, it says the peak amplitude of this AC generator is actually 226.3 volts peak amplitude. If you multiply that by 2, that's a very large AC voltage that's present on the source there, which is a really dangerous level of AC. It's 60 hertz, but the idea is that if you want to try to avoid hobbies that involve real transformers, basically. When you design rectifiers, you're probably going to design them off of another DC supply. Designing these circuits using transformers, it's very basic. It's something you probably need to study transformers a lot before you try to use them. But we'll assume that we're going to build this, at least in theory, the way it's shown. So the diode current IZ-min is 0.5 milliamp. Use a practical model for each diode, assuming the diodes turn on at 0.7 volts if it's on. So we can bring in our formulas. The line peak voltage, 226.3 volts. The source peak with the transformer 1 to 10, 22.63. The capacitor peak voltage is the VS peak from the transformer minus 2 diode drops. So it's 22.63 minus 1.4. So the peak capacitor voltage is 21.33 volts. Now this, when the AC comes out of the this part of the transformer, which dial does it pass through?
D1?
Five?
D5. D5 is forward bias. D1 blocks the AC. So the AC will come over here and pass through D5. Now what happens to the AC? How does the AC get back to this point? This is the return for the AC. It's got to complete a loop. So it has to complete the upper part and the lower part. We're on the upper part now. So we just completed this part. And notice this diode blocks the AC. So the AC is still trying to find a path to ground. And this is kind of one of the unusual parts about this, is that how does the AC actually get through this system? The only practical path to get to ground is AC actually passes through the ground and then goes through D3.